Okay, guys. So to bring you up to speed to the conversation that Nick and I are having up here. In most cases, I'm going to be recording second period because, well, if I make a mistake or the computer dies, which happens a lot, this thing has a battery of about 40 minutes, then I can just redo it again later on. So most of the time, you guys are going to be the ones that are going to be recorded unless something goes horribly wrong. And then I take those videos and I upload them to your tube and link them to Google Classroom. So if you want to watch the lecture all over again, or you don't want to take notes, you just want to watch the lecture to study, that's perfectly fine with me. If you're one of the people who wants to take pictures of each slide because reasons, then I'm fine with that too. If you want to write everything by hand, great. I'm totally cool with that too. Whatever method helps you to learn the material, I'm into. I will never check your notebook. Okay? I will never check your notes and say, you didn't take notes, this is a grade. Your notebook will never be a grade. Okay? You need to prepare for a college environment, and one of the most important things that you can learn as a study skill for high school and college is knowing how to get the material into your brain. If you are someone who learns better by writing, please take notes. If you are someone who learns better by watching, then focus. Okay? If you are someone who learns better by listening, then listen, watch the YouTube, listen to it again. Okay? Put YouTube on your earbuds when you're going home on the bus. Okay? Whatever method works best for you, use that method. Questions? Okay. Now, for those who are taking notes, I apologize on behalf of the last 10 teachers you've had that told you, if it's important enough for me to write, it's important enough for you to write. Terrible. Oh, okay. If you see something on the board, there's going to be a lot of writing. Most of the stuff you don't need to know. Okay? You don't need to commit it to memory. If there's something that is really, really obvious, or something that can be easily researched, don't write it down. If something is new to you, write it down. Okay, does that make sense? Yes. So if you just turn into a pipe where the information goes in one end and out the other, my brain is just a pipe. I look at the information, I write it on the page. Then you're not actually getting anything. Pipes don't absorb anything. You should be a sponge where things come in and you hold on to it for a long time. If some spills onto your paper, great, but most of it should stay in your brain. Capiche? Okay, so again, I'm never going to check your notes. If something is really obvious, don't spend the time writing it down. A lot of what we're going to be doing is I'm going to be asking you questions. And I'm going to be saying, what is this and how does this work? And if you can't answer those questions, either out loud or in your head, then you don't know it. Okay. If you can write something in your own words, there's a pretty good chance you understand it. If you can't write something in your own words, you don't understand it. And you should ask questions. So I'm going to say things like, give me a thumbs up if you're with me, if you understand. And if you can basically say, all right, there's protons and neutrons in the nucleus and electrons. Okay, I understand, good, we're good. But if you be like, I have no idea what you said, don't give me this, just to blend in, give me one of these, okay? Because I really don't care. I really don't care how many times I have to do this. What's important is, on the test, you perform very, very well. Okay? I don't care if you look cool or don't look cool. You're like, I don't want to look cool and unask a question. Most likely, if you're asking a question, you're not the only person who doesn't know or doesn't understand. You're just the person that is least shy and doesn't understand. Okay? Are we good? Okay. Give me a thumbs up if what I said just made sense to you. Okay. If you have questions, put your hand up and we'll wave it around. Cool. All right. So, Unit 1. There's about half a dozen units you have to learn in first year chemistry. Then everything else you learn in AP. And the first one is atomic theory. So atomic theory is what goes on in the atoms. And I know you've heard the word atom before because you're all 15, 16, 17, 18 years old. And you've had previous science classes. So an atom is the smallest piece of matter that represents or has the properties of a thing. Okay? So in this unit, we're going to learn atoms, elements, and compounds, the parts of the atom. The parts of the atom are called subatomics, literally inside the atom or below the atom. And then nuclear stability. We're going to learn about how nuclear particles work. Okay. Questions? Then off we go. See my button. My button's working. Woo! All right. So, atoms. Atoms are the simplest building block of matter. Okay. And there's a whole bunch of them. Most of what we encounter in our lives are not atoms. Most of them are elements. But atoms are the simplest building block. If an atom can exist in elemental form all by itself, it will. If it can't exist in an elemental form, it'll exist as a compound. So the difference between atoms and elements is some atoms can't exist as atoms. They have to exist as elements. So whereas atoms are the simplest building block, elements are the simplest thing that we encounter in real life. Okay, for instance, oxygen, O2, does not normally exist as an atom. It normally exists as an element. Okay? Carbon can exist as an atom, but you're not going to find it in atomic form. You're going to find it in elemental form. Okay? So the atoms are the simplest building blocks, and the elements are the things that you will find in real life. Does that idea make sense? Okay. So again, there are. It's not really. Yeah. So a lot of people say there are 92 naturally occurring elements. There are only 90 because there are 2 inside uranium that are actually not naturally occurring. So once you get to uranium, which is 92, and I keep looking over there because it used to be over there, we will hang the periodic table this week, I hope. So I'm gonna probably need some help from one of my classes. Probably not this one because we have a lot of busyness to do, but we'll hang the periodic table hopefully this week and it'll be like right there. It'll be great. So once you get to uranium, which is atomic number 92, then everything after that is artificial. They're nowhere on the planet. We have to make them. Okay? And inside uranium, technetium and promethium are also artificial. So everything up to uranium can be found on the planet except technetium and promethium. Okay. Give me a thumbs up if that makes sense to you. Okay. So if I said, hey, is atomic number 101 on the planet? Your response would be no. Where do you find it?
In a lab.
In a lab, exactly. In a big lab that makes atoms. Now, there are 7 that are very, very special. And they are called diatomic. They are diatomic molecules. What does diatomic mean? 2. It means 2 atoms. Okay? Diatomic means 2 atoms, meaning you will never find a nitrogen all by itself. It will either be in a compound or in an element of 2 nitrogens. You're like, I'm nitrogen all by myself. Oh no! Hey, there's another nitrogen all by myself. They stick together. Okay? So if you find something that is diatomic, it can't exist in its simple element or simple atomic form. It has to be paired with itself or in a compound. Now there are 7 diatomic molecules, and we have a mnemonic to remember them. It's called Brinkelhoff. Brinkelhoff. It's also right there. Brinkelhoff. So if you're in the front row, you can be like, oh, it's right there, Brinkelhoff. Okay. So these are 7 diatomic molecules. They don't exist by themselves. They have to be paired with another one. So they are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Okay? They are all gases except for bromine and iodine, which are halogens, and we'll talk about those. They're right under chlorine and fluorine. Questions?
Which ones weren't the gases?
The ones that aren't gases are bromine and iodine. At room temperature, bromine is a liquid, and at room temperature, iodine is a solid. But they are right below fluorine and chlorine. Yeah.
So if they're dynamic, that means there's 2 atoms in it? Or
Diatomic?
Yeah.
Yeah. If they're diatomic elements, they cannot exist alone. They cannot exist in their basic atomic form. Like iron can exist by itself, 1 Fe. However, you can't have a single bromine. You can have a bromine attached to a bromine, or you can have a bromine attached to something else, but a single bromine can never exist. Good question. Other questions? Moving right along. Okay, so compounds are what we usually find in the world, and they're what you get when you have multiple things stuck together. So a compound is simply something made of more than one element. So our most popular compound, you're made of about 2/3 of it. so is the planet, is H2O, or so they're surrounding the planet. H2O, 2 hydrogen atoms and 1 oxygen atom. Looks like Mickey Mouse. So you got an oxygen atom, you got a hydrogen atom, and it looks like this for a reason that we'll learn later on. And if you look at it, it looks kind of like Mickey Mouse.
Yeah.
There we go. Or Mickey Pig. Here we go. Good pig. There we go. So, yeah. So, water is a compound because it's made of more than one element. Okay. Sodium chloride. This is a compound called an ionic compound, and it's popular to put on French fries. And then Fe2O3, this is what happens if you leave your shovel out in the rain. The outside will turn into Fe2O3. Just rust.
There's more compounds in this.
Oh yeah, there are billions. Yeah, those are just 3 examples. Okay. How are we doing so far? Okay. Ready to move on?
Yeah.
Moving on. Okay, so you guys know what the parts of the atom are. What we call the subatomic particles, also called nucleons. So in the nucleus, you're going to find what 2 particles? Just blurt it out. Protons and neutrons. So protons and neutrons are nucleons. They are particles inside the nucleus. And the one subatomic particle that is outside the nucleus is the electron. Okay, so you guys know all this stuff. A proton has a charge of 1 and a mass of 1. A neutron has a charge of 0 and a mass of 1. And an electron, which does not do that, is a charge of -1 and a mass of 0. They don't do that. I don't know why someone decided to show atoms like that, but that is not like atoms look like.
Can you draw some examples?
Yes, just about to. Okay, so I got the big angry bird and the little angry bird. Okay, so who wants to be the proton? Okay, Cannon wants to be the proton. There you go. And who wants to be the first electron? Okay. You need to take that. Okay, he's going to be the proton. We're going to model the hydrogen atom. Okay, the hydrogen atom is the simplest, smallest atom in existence. All right. So Cannon's got the proton. Matthew, you need to take that electron and run down to the band room. No, I'm joking. But that's where the electron would be. So you generally think of this atom as being squished together. It's not. If Cannon's got the proton, Matthew's got the electron. The first electron is like way down the hallway. That's how empty the atom is. There's nothing going on between the proton and the nucleus and the first electron. If you want another model, then you take your football and you set it on the 50-yard line, right on that giant star in AT&T Stadium, or right in that giant star. If you're a Cowboy fan, take a football and you put it right down in the middle of the 50-yard line. Then you take a tennis ball representing the atom or the electron, and the electron is on the goal line. That's how empty the atom is. It looks nothing like that, but for some reason, that's how we draw. Okay, does this idea make sense? Question.
So like in real life, or like if they were the size of a football?
Yes. If the proton was the size of a football, the electron would be a tennis ball at the goal line. Yeah, that is how to scale it would be. Fun, huh? Yeah. So very, very empty. In fact, it is often said that if you were to take all the empty space out of the world, you could fit the world into a house. It would have the same mass as the world, but you could take it all out of there. Now, in a normal, neutral, unreacted atom, the number of protons and the number of electrons are the same. The number of positive charges equals the number of negative charges in a normal, neutral atom. When that's not the case, you have what's called an ion. So for instance, I don't think we need this anymore. We can erase this. So let's look at a simple atom. The simple atom will have 6 protons and 6 electrons. Now, I'm not drawing where they are. We'll focus on where they are later. But our simple atom has 6 protons and 6 electrons. So that means we got 6 plus negative 6. So the overall charge is 0. Now, if this atom gains an electron, and there's no longer 6 electrons, now there are 7 electrons. Now we have 6 plus negative 7, and the charge is now what?
Negative 1.
Negative 1. Negative 1? But it gained something. How can something gain something and become negative?
Because since the electron is negatively charged, if it gains one more electron, it makes the entire atom negatively charged.
Exactly right. Okay, everybody hear that in the back? The electron is negatively charged. So if something that is neutral gains a negative 1, it makes the whole thing negatively charged. So in other words, 0 plus negative 1 is negative 1. Capiche? The other example, of course, is if you have an electron and it loses an electron, now we have only 5 electrons, then 6 plus negative 5 is what?
1.
1. So if you lose an electron, you become positive. Okay? Give me a thumbs up if that makes sense to you. Question?
You're on this back.
Eventually. You want to get rid of it right now? Into the fidget bin. Into the fidget bin with you. Okay? So we're good with this idea about ions? Moving on. Okay, isotopes. Isotopes are what you get when you have a different number of neutrons. So isotopes are what you get when you have a different number of neutrons. Now, neutrons have a mass of 1 but no charge. So back to our example here. Make it neutral again. Or 6 electrons. Now, if you have 6 neutrons, neutrons are usually shown with an N0. If you have 6 neutrons, then you have a total mass number of 12. Because 6 for protons, 6 for neutrons. So if you've got 6 protons, 6 neutrons, you got a mass number of 12. And carbon, this would be carbon. This is carbon 12. I know it's carbon because there are 6 protons. I know it's carbon because there are 6 protons. I'm going to need to move the camera back. Hopefully it doesn't get in your way. I want to be able to see more of the screen and then zoom out. Zoom out. That's as far as I can zoom out. Okay. There we go. Okay. This is just easier than being like, yep, I can see it. Okay. So I know it's carbon because carbon has 6 protons. All carbons have 6 protons. If it isn't carbon, it will have a different number of protons. All carbons will have 6 protons. What's the atomic number of carbon? 6. How many protons does it have? 6. Nitrogen has 7. How many protons does nitrogen have? 7. Oxygen is 8. How many protons does oxygen have? 8. You see the pattern?
Yes.
Okay. So if it has 6 protons and 6 neutrons, we call it carbon 12. However, if it has 6 protons and 7 neutrons, we call it
Carbon 13.
carbon 13. It has a mass number of 13. These are called isotopes. Isotopes are the same atom with a different number of neutrons. Okay. Now when we show nuclides of those isotopes, we show it with 2 numbers, one with a mass and one with a charge. The mass goes on top and the charge goes down below. Mass goes on top and the charge goes down below. So if we were to complete our little diagram for carbon, we would write this 12,6 carbon and 13, which number should you go down here for carbon?
I think it's
Still 6, yeah. Because carbon still has a charge of 6. Okay. So these are isotopes. Mass on top, charge down below. Symbol in the middle. Yeah. 1 and 2.
Is the charge and the atomic number always going to be the same?
No. The atomic number is the number of protons, and the charge is going to be the difference between protons and electrons. So, oh, you mean for each nucleus? For the nucleus, yes. For the nucleus, not the whole atom. For the nucleus, yes. The charge will be the number of protons. Yes, thank you. Just for the nucleus, but not for the whole atom. Yeah. For the nucleus, the charge is the number of protons. Is that your question too?
I was asking about the charge, yeah.
Okay.
So the charge is 2?
I'm sorry?
The charge is 2?
No, the charge is
The charge is 6.
So the mass.
In this case, it's 2. Okay. So in this case, the charge is 2, the mass is 4. This is a helium nucleus. A helium nucleus has 2 protons. Make that a neutron. There's a neutron, and there's a neutron, and there's a proton, and there's a proton. So this is the helium nucleus. Helium. Nucleons. So 2 protons and 2 neutrons. Okay. The helium nucleus has 2 protons and 2 neutrons. The protons are +1 each, and the neutrons are +1 mass, but no charge. So +1, and for the protons, +1 mass, +1 charge. Neutrons, +1 mass, 0 charge. So that means the overall mass is 4, but the charge is only 2. See how this works?
So the electrons aren't counted for it?
Correct, because we're only looking at the nucleus. We're looking at when you hear nuclide, that means just what's in the nucleus. Okay. How are we doing so far? Good? Now, the helium nucleus has a special name. It's called the alpha particle. We'll get to it in a little bit. Okay. So when we're talking about nuclear decay or nuclear transformations, that's when one nucleus turns into a new nucleus. This is the nuclear decay for uranium. Uranium-238 has 92 protons, 238 total mass units. You could subtract to find out how many neutrons there are. Alexa, what is 238 minus 92?
238 minus 92 is 146.
Okay, so there's 146 neutrons and 92 protons, giving us an overall mass of 238. Make sense?
Yes, sir.
Okay. So what's going to happen is that uranium is going to go burp. It's going to burp out an alpha particle, a helium nucleus. And what's going to be left over